Okay, continuing with the discussion of the symmetric slab, and believe it or not, I'm almost done with the symmetric slab as far as the theoretical development goes. And so now I have beta is equal to k sine theta, which is the longitudinal wave number. It's kind of like k, except it's for inside the waveguide. And we have that omega over beta is equal to c by n1 sine theta, which is c by n effective. In other words, n effective is equal to n1 sine theta, and this is equal to the propagation speed of energy in the waveguide. Okay? It characterizes. So this is the propagation speed in the waveguide. I'm sorry. And characterizes it in the same way that the refractive index always characterizes the propagation speed. Notice now, let's go ahead and evaluate n effective for the case of theta is equal to 90 degrees. Then, well, the sine of 90 degrees is 1. N effective is then equal to n1 sine 90 degrees, which is equal to n1. In the case of theta equaling the critical angle, which is the other extreme, remember that in our plot, in our mode plot, we have to keep theta in the range from theta critical up to 90 degrees because these are zigzag rays that we're assuming are undergoing total internal reflection. Okay? And so the other extreme is the critical angle, and in this case, the n effective is n1 sine of the critical angle. But the critical angle is the arc sine of n2 over n1. So this is easy because this just reduces to n2. So now we see this really nice result. That the effective index is in between the lowest possible value n2 and the highest possible value n effective. Okay? And we also can see then that this is correspondingly to the fact that theta is in between the critical angle and 90 degrees. Okay, so what I'm going to do then is I'm going to take my mode plot, which was previously theta versus d by lambda. I'm going to now redo the vertical axis to be n effective. And I can do that and I will make my mode plot go from a low of n2 up to a high of n1, and these again form the asymptotes, and I will have evenly spaced points along the axis here of d by lambda. Again, d by lambda is called the dimensionless or unitless waveguide thickness. Okay, where this spacing is delta d by lambda at the critical value, which is 1 over 2 square roots of n1 squared minus n2 squared. Okay, and these are all evenly spaced. All right. And this is the m equals 0, 1, 2, 3, 4 mode. Okay, this is a nice result. We can, if we calculate this first curve here, for example, in a spreadsheet, then we can calculate all the others because we know the spacing of these modes. For example, if we go up to this value of theta, then this spacing is also known. This spacing up at any angle, not just at the critical angle, is given by 1 over 2, 2, and 1 cosine theta. Okay? So this is for any theta. Okay? So this is the final result that we get on our slab waveguide, and I think I've given you all of the essential ingredients. These values of d by lambda are called the cutoffs. Okay? And what I'll do now is I'll explain a little bit about mode cutoffs and mode confinement. Actually, I won't. I will end this video here and come back to that topic. Thanks.